So now we know how HF, or frictional head losses, relate to the shear stress at the wall. So the question is, how do we find our shear stress at the wall so that we can find the HF? Well, one option is analytically. If we can find an equation for our velocity, then we can find our equation for shear stress at the wall, which is, remember, mu du dr, and at the wall, it's r equals 0. This is only possible if we can solve those laminar Stokes equations, right, to get that u. And that is only possible for laminar because turbulent is unsteady, and there's no way we're going to be able to solve it. Unsteady 3D, it's a mess. We're not going to be able to solve Navier-Stokes for that. But if it is laminar, we can still use our laminar flow solution, which in terms of u max was u equals u max times 1 minus little r squared over big R squared, where big R squared again was the radius of the pipe. Okay, so if we take the derivative of this, du dr equals minus 2 u max times r over big R squared. And that then, if we don't want to use u max, if we want to use v average, remember v average was u max over 2. So we can say minus 4v, because u max was 2v, times r over big R squared. Okay, so that is our du dr. Okay, so our wall shear stress, just plugging that du dr into our equation then, is, well, first of all, tau everywhere is going to be mu du dr. And so that's going to be minus 4 mu v times r over r squared. And to get at the wall then, and let's just do the magnitude at the wall because we already included the sign before in our conservation of linear momentum equation, knowing it was going backwards. So our shear stress at the wall then, dropping that sign, 4 mu v over big R. Or let's put it in terms of d, 8 mu v over d. All right, so we can calculate our shear stress of the wall if it is laminar. Okay, if it's not laminar, then we're going to have to go to experiments. Okay, so we can use, since it's experiments, we can use our chapter 5 stuff. So what we want to do every time we do experiments is put things in non-dimensional form. So for shear stress, we figure it's a function of rho, mu, d, velocity, and epsilon, where epsilon is wall roughness. Turns out wall roughness doesn't really matter for laminar flow, but for turbulent flow it is important. If we go through our whole finding the pi group method, Ibsen pi method, we're going to come up with tau at the wall over rho v squared equals a function of Reynolds number and epsilon over d, because epsilon is a length scale. Okay. Let's instead, we can, how we can flip non-dimensionals, we can actually multiply constants by it. So let's call this factor here times 8 tau wall, 8 tau wall over rho v squared. What we're going to call that is F, or the Darcy friction factor. Okay, don't get that F mixed up with this F. This is the F that you'll find in that HF equation. Okay, and it's still non-dimensional. Okay, so our Darcy friction factor for laminar flow, we can figure that out directly. So remember F equals, we said right here, it's 8 tau the wall over rho v squared. Well, we have an equation for tau at the wall, so that's going to be 8 times 8 mu v, okay, over our rho v squared d, okay, and one of these v's cancels. 64, 8 times 8 is 64 mu over rho v d, all right, which happens to be 64 over Reynolds number. All right, So that's all you use if it's laminar flow. So if you figure out you got Reynolds number less than 2300, you can just use that for your F, for your friction factor. Okay, now how does this then relate to HF? Well, we already found out that HF was equal to 4 tau the wall times L over rho GD. Okay, so plugging in our F here, we're going to get 4 F rho V squared L over 8 rho GD. Okay, so that's taking our equation for shear stress for laminar. Okay, tau wall. Okay, so now we can simplify this a little bit. Rows cancel, and we are going to get FLV squared over 2DG. Right. Actually, that's not just laminar. That was from this tau wall, this equation. Okay, so we can't find F for turbulent flow from Navier-Stokes. So we go to experiments, and someone back in 1944, L. Moody, did some experiments with pipes and came up with the Moody chart. Okay, the Moody chart is what we use to find F. So basically find your Reynolds number, find your roughness value, go over where these lines meet, and then you can go and read your friction factor from the left. Plug that in and find HF. That's how you use a Moody chart. Someone has done a correlation for the Moody chart. In other words, turn all these lines into a single equation, and what they get approximately is this equation for F. That is log base 10. Okay, so there it is. A lot of times it's a pain to plug into that equation. So if you have Reynolds number, then it's a lot easier usually just to read it off the chart. And both of them are only have an accuracy of like plus or minus 10%. So it's not all that great either way you go. So don't think that using the equation is going to make it more accurate. As long as you read the Moody chart right, then that's just fine. Okay, stop here and do quiz questions 3 and 4.